Alright, welcome back. So, this is 8th lecture in this course. My name is Himanshu and we were discussing different types of random variables. So, in this lecture, we are going to talk about continuous random variables. So far, whatever examples we have covered about probability assigner functions, they were the cases where our sample space was discrete. Okay, so the outcomes that we were interested in were of this type, either yes, no, heads, tails, or the number of road accidents, right? So those were all the cases of discrete outcomes, right? But what if you have continuous type of outcome? Okay, so what could that be? So for example, you are doing similar kind of experiment where the participant have to recognize that the word shown on a screen is a meaningful word or not, or it's a meaningless string. Okay, they indeed have to give yes and no response. So if it is a meaningful word, they would say yes. If it is a meaningless word, they would say no. Okay, but let's say what you are interested in is the amount of time they take to give a response. Okay, so you can call it the recognition time. Okay, so in how much time, how quickly they give this response. Okay, why you would be interested in this? Because you might be testing a theory which says that if it is a meaningful word, then participant quickly recognizes it, right? They wouldn't take a lot of time to recognize it. If it is a meaningless word, then the participants, let's say, search through whatever they remember, search through their dictionary in their head, and they can't find that word, so they take more time when it's not a meaningful word in English, right? So if it is a proper word, then the recognition time should be faster. If it is not a word, recognition time should be slower. So theory can say that. So if you are interested in such a theory, you would record these recognition times. So how much time do they take to recognize whether a string is a meaningful word or not? Okay, so the participant sees these strings on a screen one by one. So sometimes they would see a proper word, sometimes they would see a non-word, and their task is to recognize whether it's a word or non-word, and we are recording how much time do they take to recognize a particular string as word or non-word. All right, now given that you are interested in these recognition times, okay, if I ask you what would be your sample space? Okay, so what are all the possible values that the outcome can take? So what are all the possible outcomes in a, let's say, in a particular trial? Okay, so what are all the possible outcomes here? Is, let's say, 300 milliseconds, a recognition time of 300 milliseconds, is it a possible outcome? Yes. Is a recognition time of 255.55 milliseconds, is that a possible outcome? Yes. In fact, you can think of that it could be anywhere between 0 and infinity. Okay, so it could be in fact set of all positive real numbers. So anywhere between on this number line between 0 and infinity, okay, any point on this number line is a possible outcome, right? So it could be a fractional value as well. It could be, let's say, 255.55, something like that, right? In fact, there are infinite number of possible outcomes here, right? So your sample space can be said to be, let's say, a set of, if you don't want to include 0, it would be a set of positive real numbers, right? Now let us see how 3 axioms would apply here. Okay, so by the way, so this is now continuous. This sample space is of continuous type, right? There are no discrete values here. Okay, the possible outcome could be anywhere between 0 and infinity, and there are infinite number of possible outcomes here. So this is a continuous sample space. Okay, so let us see how we work with such continuous sample space cases. Okay. So let us try to apply the first axiom. Well, the first axiom says that probability of any event would be greater than equal to 0. So any event that is a, let's say, a subset of your sample space, its probability would be greater than equal to 0. Okay, so what kind of events can exist here? You know what is the sample space, what kind of events can exist? We actually have briefly talked about this in one of the previous lectures. So, one type of event that can occur here is that any point on this real number line would be an event, right. So, if I talk about this particular set, a set containing only one member, let us say 300 milliseconds, a set containing only one member 255.5 milliseconds, a set containing only one member 0.75, right. These are all possible events. What kind of events are these? These are elementary events because they contain exactly one member. Okay. So, what would be elementary events in this case? Any point on this real number line would be an elementary event. Okay. So, the first axiom would apply to all these elementary events. Okay. So, that means the probability of obtaining a reaction time of 300 will be greater than or equal to 0. Okay. That is the first axiom, that is what first axiom says. Okay. So, probability of any point value would be greater than equal to 0. Okay. What are the other kind of events that can exist here? What is an event, by the way? So, an event is a possible subset of your sample space. Okay. Now, all these points are possible subsets of your sample space, okay. But you can think of another kind of subsets, which are that any segment, any line segment or any interval, okay. So, any interval on this real number line. So, let us say this interval between 200 and 300 milliseconds. Okay. So, an interval between 200 and 300 milliseconds. You can call this event, this is an event where you obtain a recognition time between 200 and 300 milliseconds. Okay. So, this is a possible event. Okay. And what is this? It is a interval on this real number line and it is a subset of your sample space. You can say this is a subset of your sample space, okay, and it is an interval on this real number line. So, this is also another kind of possible event. So, you can think of intervals on this real number line as possible events, right. These are not elementary events, but they are still events. So, you can think of that probability of obtaining a recognition time between 200 and 300 should be greater than equal to 0. Same goes for any other event. Let us say probability of obtaining anything between x1 and x2 would be greater than equal to 0. Alright, so that is what the first axiom says. Now, let us see what second axiom would imply. Okay. What is the second axiom? That one of the elementary events must occur. Okay. What are the elementary events here? All the point values on this real number line. Okay. One of that event must occur. Okay. Which makes sense, by the way, because whenever you are doing an experiment, you would obtain one of the point on this real number line as your outcome, right. But problem here is this, that you have infinite number of such points. Okay. Then what would second axiom give you? Let us see. So, what second axiom says is this, that let us say x1, x2, x3, xn, these are all the points on the real number line. Okay. How many points would be these? Actually infinite. Okay. So, this n is infinite. How many points would be there between x1 and x2? Infinite. So, you do not know, right. So, according to second axiom, probability of x1 union x2 union x3 union xn should be equal to 1. Okay. So, probability of union of each elementary event should be equal to 1. Now, let us go to third axiom. By the way, here you should write it like this. So, they are dot 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 between these x2 and x3 because infinite number of events between x2 and x3 as well, right. Now, let us go to third axiom. Third axiom says if two events are mutually exclusive, or let us say any events are mutually exclusive. So, let us say xi intersection xj is phi, right, it is an empty set, then the probability of x1 union x2 union x3, these are all mutually exclusive events. Okay. In this case, what we can say that all the elementary events at least, okay, we can make this statement at least all elementary events, that all the elementary events are mutually exclusive. So, you can write this, that union of these elementary events would be equal to, a probability of union of elementary events would be equal to summation of their individual probabilities. Okay. So, that is what the third axiom says. Okay. And from second axiom, you know, so that you know that probability of union of elementary events is 1. From third axiom, you says that probability of their union equals to summation of individual probabilities. So, based on these two axioms and the first axiom, what you can write is this, that probability of x1 plus probability of x2, in fact, I should write that there could be infinite points between x1 and x2 as well. It is a probability of x2 plus probability of x3 plus probability of xn. This should be equal to 1. That is what you have derived from second and third axiom. Also, these individual probabilities x1, probability of x2, all these should be greater than equal to 0. Okay. Now, how many such elementary events do we have? Infinite. How many elementary events we have between x1 and x2? Infinite. How it is possible that the summation of their probabilities is equal to 1 and also their individual probabilities are greater than equal to 0? This can only hold if each of these individual probabilities tend to 0. Okay. So, that means in the case of continuous random variables, probability of any elementary event, probability of any point value in your sample space is going to be equal to 0. This is what the three axioms apply, that the probability of any point value would be equal to 0. Okay, which is kind of uh, like it is very different from a discrete random variable, because in a discrete random variable probability of any point value is determined by your probability mass function, but here probability of point value is already 0. Okay, then what kind of probability assigner function would you need? Okay, so let us come to that. So, what would a probability assigner function look like here? So, we need a probability assigner function which would assign a point value of 0, but it would assign some non-zero probabilities to intervals. So, let us say probability of an interval between x and x2 would be greater than equal to 0. So, it would assign some non-zero probability to the intervals. Okay. So, how do we do this? Well, although in this situation you cannot define a probability mass function, because what probability mass function does is that it directly assigns a probability value to an elementary event in your event space, right. But here the probability of elementary events is 0. Okay. So, what you do instead is this, that we do not have a probability function that can directly assign probabilities to point values, but we can think of an abstract concept called probability density. What this probability density will do, that you can define a probability density function. Although you cannot define probability mass function, you can define a probability density function on the values of a continuous random variable x, and it would be a continuous function, by the way, because x would have continuous values, such that if I would want to find out the probability at any point value of x, then it would be 0, and if I would want to find out probability of an interval of values of x, let us say between this and this, then it would be non-zero. How that can be possible? It can be possible if you apply third axiom here and say that probability of an interval of values of x, let us say x1 being between x1 and x2, is given by area under this probability density function fx. So, fx is a probability density function, we call it PDF, probability density function. So, area under this probability density curve between x1 and x2. Okay. So, this thing would give us probability. So, this is probability mass between x1 and x2. It was given by area under the curve between x1 and x2, right. Would it ensure that the probability of point value 0? Well, it would. What is the point value at x1? What is the area under the curve between x1 and x1? Well, it would be 0. There is no area at a point value between x1 and x1. Okay? This would be 0. Okay. Now, you can directly apply the third axiom here. So, let us say you want to, let us say you have another area, let us say you have another segment, line segment between x2 and x3. So, there is a segment between x1 and x2 and another one is between x2 and x3. Okay. So, what is the probability mass between x1 and x2? It is given by this. What would be the probability mass between x2 and x3? So, between x2 and x3, it would be given by this. So, area under the curve between x2 and x3, fx dx, right. Now, the third axiom will apply here because x1 and x2 and x2 and x3 are mutually exclusive. There is no common area between x1, x2 and x2, x3, right. So, if you apply third axiom here, you can say that probability of obtaining a recognition time between x1 and x3 is given by probability of obtaining a reaction time between x1 and x2 plus probability of obtaining a reaction time between x2 and x3, because these two events are mutually exclusive, right. So, you can write it like this, is area under the curve between x1 and x2 and area under the curve between x2 and x3. Okay. All right. Now, you can apply the same property to think what would be the area under this whole curve, area between minus infinity. In this case, we were interested in area between 0 and infinity. So, what would be the area between 0 and infinity? Because that is our sample space, those are the values x can take. Well, if we think about, this is our function f of x. Okay, so, this is a probability density function PDF. So, if we take such small segments, right, of width dx, right, and the point here is basically x and point here is x plus dx, right, and the height of this segment would be f of x, right, and width is dx. Okay. So, that is the area of this particular segment, right. If I keep on adding such a strip of width dx, these all strips are of width dx, okay, and I sum them up, okay, what would I get? Okay. So, the point is that if you can think of that the probability of whole space, like all possible outcomes between 0 and infinity, basically probability of sample space is equal to 1 according to second axiom. Okay. So, if I apply this to all these strips each of width dx, right. So, if I integrate all these strips from 0 to infinity, okay, I am basically summing up all these areas, right. So, that is what the third axiom says, right. So, you can sum up all these areas because they are mutually exclusive, right. So, you can basically then integrate from 0 to infinity. So, this would be equal to 1, that comes from second axiom, right. So, this is what you know, that area under this probability density curve would be equal to 1, okay, from second and third axiom. Okay. So, for continuous cases, we are not going to define a probability mass function. Okay. what we are going to do, we will have to assume a probability density function. A probability density function is a function that assigns probability densities to the values of your random variable. It does not assign probabilities, it assigns probability densities to the values of a random variable. What is probability density? It's an abstract concept which means it's the how likely is that particular value of x is to occur, right? It's related to probability, but it's not exactly probability. It would tell you the likelihood of occurrence of a particular value of the random variable, right? And if you multiply this probability density with an interval and you integrate it, then you would get the probability mass. So, probability mass is the area under the probability density curve. Okay. So, for any continuous random variable x, you will define a probability density function. Let us say f of theta x, or if you are used to write in this order, f of x theta. Okay. So, where f of x theta is your probability density function. Okay. Now, probability of any point value of x would be 0 that we have derived, and probability of value of any interval, probability of observing an outcome between x1 and x2 would be given by area under the curve under this probability density curve with respect to theta, with respect to parameter, or with respect to x. So, um, this is how we can work with continuous random variables. Okay. So, we will now take a look at some common examples of continuous random variables that we will use later on in this course, and those are also the very common and basically um, frequently used continuous random variables, frequently used probability density functions that you will be using in your data analysis as well. Okay. So, you might have heard already about some of them. So, for example, one of them is a normal random variable or a Gaussian random variable. Have you heard about normal distribution? Yeah. This is a case of a continuous random variable. Okay. So, let us say you have a continuous sample space, okay, such that a sample space omega that can take any continuous value between 2 points, let us say minus infinity and plus infinity, right. And you can define a random variable x that takes values between minus infinity and plus infinity, right. It takes values between minus infinity and plus infinity. Now, the probability density assigned to a particular value of this random variable x, okay, can be given by a normal random variable with two parameters, mean and sigma, okay, such that probability density function is given by this 1 by root 2 pi sigma square e to the power minus 1 by 2 x minus mu by sigma whole square. So, this is the probability density function of a normal distribution. Yeah. But of course, it should follow a certain property, only then it would make sense to assume that a particular random variable has a normal distribution, right. We will see what are those properties. For example, think about the recognition time experiment. Okay. So, in the experiment where participants have to recognize whether it's a meaningful word or not, we are recording their recognition times, right. So, can you assume that recognition times come from a normal distribution with mean mu and standard deviation sigma with these two parameters? Okay. How would you think that? How would you decide that? Whether recognition times come from a Gaussian generative process. Okay. If that assumption is reasonable, if that makes sense, only then you can assume that recognition times come from a Gaussian process. By the way, this is the often taken assumption in these recognition time studies, that these recognition times are normally distributed. Okay. But this assumption can be wrong, okay, and we will see how. Okay. So, in the next lecture, we will go into detail of normal distributions. What exactly is the property of normal distribution? In what situation you can assume that a random variable has a normal distribution, right? And what is its PDF, and how we can use it in R. All right. Thank you very much. I will stop here for this lecture. In the next lecture, we will go into details of normal distribution and some other continuous random variables like a beta random variable and a log normal random variable. All right. Thank you very much.